So Lewis electron dot symbols of atoms and ions, bonding made simple. That's really what this is. It's a very simplistic, but it works. And you can make some really strong predictions using Lewis electron dot symbols. And we're going to be able to predict that water's bent. We'll be able to predict that carbon tetrachloride is nonpolar. I mean, all of these things about very small microscopic systems, you can make some really powerful predictions. And actually how they even look. But Lewis electron dot symbols, it's pretty much all right here. Kind of shows you how to draw them all. Annabelle. This is how you draw Lewis electron dot symbols. It looks like you pretty much just do what? To draw a Lewis electron dot symbol. Yeah, put dots next to the symbol. Now how many? Now the dots. How many dots? Number of valence electrons, which is always the what number? What do they call these? There's the G, the group number. And we're not supposed to say dots. We're supposed to say valence electrons, like Christian said, right? And they're kind of spaced out, kind of symmetrically, and that's nice. We'll do that too. Later on, it'll help us in the future, okay? So let's delve into this. Daisy, I'm going to ask you for a chemical formula of any salt or ionic compound. Now, when you do that, there's a trick to it. You can pretty much name anything you want. Just don't give me a what up there on the periodic table. Otherwise, well, no, you better give me this. You better give me this, otherwise it won't be an ionic compound. Starts with an M. You better give me a metal. You better give me a metal, right? Otherwise it won't be an ionic compound. And you can't say sodium chloride, because everyone says sodium chloride. And remember, ionic compounds are always a cation, some cation, and then some anion. Potassium chloride, right? Whoa. Right, some cation, some anion. She says KCl. Okay. So I see a metal, potassium, so it works. Okay. Ionic bonds hold the atoms in potassium chloride together in a crystalline form, Jorge. Just what is an ionic bond? I mean, this is stuff, and yeah, it's really small, but something's holding this stuff together. What's holding it together? Something's causing it to stick together. Anyone help them out? Electrons are kind of part of it. I see cation plus, anion minus. What do you call that? Plus and minus? Well, magnet would be, that's the magnetic field. This is more like an electric field kind of idea. They call it kind of like electrostatics or something like that, right? Where, you know, plus and minus stick together. Right? There's an attraction between there. Is that a strong attraction? Plus and minus. Yeah, it is, right? So these are going to have really high melting points, those things. How about a molecule? Now, Allison, when you give me a name of a molecule or any chemical formula of any molecule, just don't give me a what, and you'll be okay. Don't give me a metal. Don't give me a metal. Otherwise, it's going to automatically be an ionic compound. So pretty much any nonmetals, and throw them together. There really is no wrong answer. Remember where the nonmetals are? No? Right? I wish we had that kind of step ladder thing going, right? Kind of goes along here somewhere. So all of this, all of these are what? Everybody. metals. They all form cations or anions. They all form cations. They're all positive. So here's our anions, or our nonmetals. Just pick them, throw them together. Anybody help her out? A C and an S. Carbon, I heard CS2 or something, right? Doesn't matter. We'll worry about later in more advanced classes as to whether this stuff can actually exist or not. Okay. Two nonmetals. We threw them together. How do we name that? Melissa, how do you name that? See, we're going to have to take a final exam and remember all this stuff, so might as well review as we go here. How do you name? We're not supposed to say CS2. We're supposed to be able to count to 10 in Greek. Not dicarbon. Monocarbon disulfide. Monocarbon disulfide. Okay. What's holding these atoms together? And again, later we'll be able to predict whether it's bent and linear and all that kind of stuff. But Erica, what's holding this stuff together? And they're really small, but something is holding them together. And it's an abstract idea. Does anyone know? They say that a lot. They call that a lot. They're sharing electrons. And it's really hard for my brain to visualize sharing electrons. Okay, we're going to share an apple juice. What the hell? That has nothing to do with things sticking together. I don't picture that at all in my head. So instead, I like the quantum mechanic picture. And we said that all these atoms have these, starts with an O, that the electrons are in. They stay in there 99.9% of the time. Orbitals, clouds, right? So this guy has his electron clouds. This guy has his electron clouds. This has his electron clouds. But it looks more like they have to overlap. There's a big mess, right? Who knows what the shape is of this thing? And nobody knows whose electrons are whose. These electrons are all intermingled. That's what's holding the whole thing together. And yeah, you can call it sharing, but I kind of like the idea of just a big, ugly mess that's a cloud of orbitals, right? And it's just, that's what's holding it together. It's not as strong as electrostatic, but it's pretty strong. It can be, especially if it's in the right orientation, like diamond. Okay, Lewis electron dot symbols for atoms and ions. Okay, we already kind of talked about how you write them. So let's go ahead and write a few. Let's write the Lewis symbol, Jonathan, for carbon. How would you write the Lewis symbol for carbon? Right. Anybody help them? Write a C with 4 dots. 4 dots because carbon has how many valence electrons? 4. And you just look at the periodic table to figure it out. Right? Carbon has 4 valence electrons. C+1, Tegan. How would you write the electron configuration for C+1? Sorry, the Lewis symbol for C+1. She says a C with 3 dots. Do you agree? Yeah, because it has 1 less than it's supposed to. It's supposed to have 4. It'd be nice if we did stuff like this and wrote charges all the time, because it's supposed to have 4, so it has 0. All the electrons match the number of protons, so it has 0. You take 1 electron away, you're short 1, so you have an overall +1 charge. But they never write the zeros, right? But they do expect you to write the brackets and charges if it's not 0. So you got to do that. So we can erase, we can get rid of this. Not supposed to have this. Shall be, how about C-4? Are there no dots?
I mean, C-4, you
add 4 extra dots. So we better have how many?
So
8. 2, 4, 6, 8. And better draw brackets and a -4. It's got 4 extra. Okay. Alejandro, way back when we were naming compounds and we did these little tricks and we said that carbon always forms what ion? All right, how do we do this? Here's carbon. It always formed what ion? First, was it negative or positive? It was negative because it's a nonmetal. C negative, how do we figure this out? C negative 4. Could we just count it over everybody to the nobles? That's 4. So C negative 4. And why did we do that? Because then carbon has an octet. How many valence electrons does every single noble gas have? 8. If you're ever going to draw any Lewis symbol, you have to draw 8. So 8 is the magic number. 8's the octet. 8 is super stable. Won't react with anything. Everything wants to get 8 valence electrons. That's why carbon is C negative 4. Not C negative 3, not C negative 2, nothing else. It goes to C negative 4. Okay. Let's see if we can answer some questions here. Why does aluminum form Al plus 3? Let's find aluminum. Let's see. Aluminum is right here. Why would you say, Christian, aluminum forms the ion Al plus 3? It wants the octet by neon. And to do that, it has to lose how many electrons? 3. There's 1, 2, and there's a third. It wants to be like neon. Good. Okay, so that's how you get Al plus 3. The next question is gallium, indium, and tellurium only form plus 1. Gallium, indium, and tellurium only form plus 1. They're right here. We've been taught since the beginning of time that, all these elements in the same group are supposed to have the same chemical properties. So this shouldn't everything have a plus 3. No. Gallium, indium, and tellurium only form plus 1 in nature. The answer is on the periodic table. Diana, why is that? The answer's on the periodic table. Yeah, they're metals. They're going to form a plus, but they don't go all the way. Like you'd say, gallium, according to what we're saying, gallium should go all the way back to argon, right? And that's to a noble gas. But there's other things that were also stable. I hope I spelled this word right. What was a pseudo noble gas core? It's supposed to be not as good as a noble gas core, but it was still super stable. What was that? D10s. D10s. You name your D10. Right? So gallium, indium, and tellurium, they lose 1 electron, boom, they're at D10. Stop. Nice and stable. So that's why they only form plus 1. Just 1 electron. Okay. How about tin and lead form plus 2? Tin and lead form plus 2. Let's see here. Tin and lead, they form plus 2. Why would that be, Danielle? Why would tin and lead just form plus 2? Does anybody see it? Why? Yeah, it's the same idea. They're just going to lose 2 because then they'll hit the pseudo-noble gas core. Exactly. Very good. 1, 2. So plus 2. And it'll have its pseudo-noble gas core. Okay. What ions would you predict for nitrogen. Annabelle, nitrogen. What ion did nitrogen form? And count over to the nobles. And 3, is it negative or positive? Negative, exactly. Right? Because it has to, where's nitrogen? Nitrogen is right here. So it has to gain 1, 2, 3. Because it had 5 valence. Or you can look at it this way. This is really what we're doing now. You want to get to 8. You've got 5, so you get 3 more electrons. Then you'll have the octet. So n minus 3. What did we call n minus 3? We got to take a final exam. I'm going to remember this sooner or later. What do we call n minus 3? Nitride. Yeah. How about oxygen? Oxide. Daisy, what was the charge? -2. Fluorine, everybody. F with a minus, and it's called fluoride. How about phosphorus? -3. And it's called, Jorge, what do you call it? P-3. Phosphide. Phosphide. S, everybody? -2, and it's called sulfide. Cl with a negative chloride. Okay, so that's just making octets. This is an oddball question, more like an anecdote. I guess I'm preparing you for that show that I like, Are You Smarter Than a 5th Grader? Right? So the question is, okay, what ion does, they pick one, and they say, what charge does it form? And your best guess is +2. Your best guess is +2. And why is that? It's not a very easy question. All of these are the transition metals in the first place, right? These are the transition metals right in here. And they all have in common 4s2, 5s2, 6s2. They all have in common s2. So those s2s can get promoted. And what it comes down to is, I don't know if you caught this in the homework. Let's say if you had something s2, because they all are s2, and this guy was d8. Okay? So you can call it 4s2, 3d8 or something. So you go through, and what guy is that? That'd be copper, right? Okay? It's wrong. The answer you're supposed to write is what? Whenever you can make the pseudo, you do it. So you can write 4s, promote these, and have them go right there. So you make your d10. 4s0, 3d10, right? So whenever you can make d10, you do it. So this is the ground state for copper. How about, then there's another one. So when you can make d10, you do it. The other situation is, let's say you had 4s2, 3d3. So that would be like vanadium. Okay. That answer's wrong. You can't make d10, but you can make d5. And if you want to write the 4s part, you can. Otherwise, you don't have to. So d10 and d5 you make when you can, okay, to get the ground states. How if you remember this? What if I had to fill that d5? I need 5 orbitals, 1, 2, 3, 4, 5. Now, how was I supposed to do that? If this is the orbital diagram, you had to put in the arrows. You have to fill it with 5. They all had to be what? Same direction and in different orbitals. So I don't know, point them all down. I don't care. Okay. That was whose rule? Hund. Okay, that was Hund's rule. How about if I had this guy pointing up? Is that possible? Yes. It's just not the ground state. What's the word for this? Starts with an E. A what state? Anything other than the ground state is called an, as long as it's possible, an excited state. So I don't know if that matters. But that's possible. But that's not how you're supposed to do it. What if I put it down? Is that possible? Is this it's possible. Is it the ground state? Nope. Okay, how do I make this impossible? What am I going to do now? Have them both down. Not possible because of whose rule? The P guy. Pauli exclusion principle. 2 electrons have the exact same quantum numbers. Can't do it. Okay, that was just a little review. See if you remember that. Okay, where are we? All right, so we can go to the boards and do some questions and then call it a day. All righty. So we want to write the noble gas core notation for each ion. Iron plus 3. And remember the D10 and D5 tricks. Just be careful. They're probably in there. Write the noble gas core notation for iron 3. Pretty much, yeah, you need the periodic table. I do. Unless you can memorize the Aufbau principle. Remember that? I don't think so. I don't want to do that either. So find iron and see what its noble gas core is. All right. I see it's argon. Then you have to write the rest. Remember doing that? So you pretty much start with argon and then finish it. It's iron plus 3. So it's plus 3 though, so you're really, the technical jargon is, you are writing the electronic configuration of, iron plus 3 is isoelectronic with vanadium. So you are really writing the electron configuration of vanadium. All right? So I see a lot of 4s2, 3d, 3d3, right? Because you have to go back. And then before you go on to the next question, you look at it and say, hey, can I make a D10? No. But can you make a D5? Yeah, so you do it. You do it. Okay. And you can write 4s0 if you want, but it's not necessary. Do the same for indium-1. Do the same for indium-1. Yeah, you have to write it all. You have to write it all. What you're thinking of is valence electron configuration. That's when you leave out this stuff.
Okay.
Okay, did everyone agree for indium? Indium plus 1, you should end up with 5s2, 4d10, right? So if you got it, go ahead and write the Lewis symbols for phosphide and gallium-1. They like dots instead of circles. Phosphide and gallium-1. So phosphorus has 5 valence, but you have to give it 3 extra, right, to make the -3, so you should have 8. Right? And don't forget the brackets. I think that's what I see mostly everywhere. 2, 4, 6, 8. And don't forget those brackets with the -3. And do the same for gallium-1. Gallium had 3. You just forgot to erase 1. I'm not sure where you're at. If you write up on the boards, I can see what you're doing. So gallium had 3. You got to erase 1 to give it the +1. Right? So we're going to agree? Let's try this third one. I helped you out by writing kind of a little skeleton of what's going on for these. So use Lewis symbols to represent the transfer of electrons between the following neutral atoms to form atomic ions with noble gas configurations. So on this side, you want neutral atoms. So you pretty much just write the Lewis dot symbol for that stuff. And then on the product side, here's where you have your ions. Very stable ions. They're very stable because they have the noble gas core notation. They match a noble gas. So first just write the Lewis dot symbols for the reactants. And then pretty much you show how the electrons get transferred. So what's going to happen? Bromine wants how many? 8. So he's going to rip off one of these. And calcium wants to lose how many? 2. Right? Do you see this? What it's trying to show is bromine wants 8. So all I need is 1 more. Calcium wants to give up 2. So that's why there's 2 bromines in there. That's really why we form CaBr2, right? Because it's a +2 and it's a minus. That's really why we have that formula of that ionic compound. And then do the same for the potassium and iodine. Yeah, that's why it forms CaBr2, right?
So
No, it's fine. This is how the format works. Or you could just write a plus and have this be a negative and a +2 and a negative. But it's all good. It's all good. +2, because it lost 2 electrons. Mm-hmm. Very good. Okay. In EX4, I changed C and D to AG and AG +1, so that's kind of different than what's in your book. So if you didn't get EX3, just ask. Yep.
Or writing the Lewis symbol for with the noble gas, or do you write it just right here?
Yeah, you just write AS with the number of dots around it. No, they want the noble gas core notation. When you start taking things out, that's valence.
Okay. So then
When you want the superscripts to add up to be the group number or the valence electrons, that's when you don't write D10.
you just write.
But this wants the full thing, right? This wants the noble gas core electron configuration, so everything. But starting with the noble gas. So for arsenic, it'd be argon. Right? And then what did you say, Daisy? You said 4s2, then what? 3d10, and then what? 4p3. Good. Looks right to me. Then write the Lewis symbol for it. Arsenic with 5 valence electrons. You can kind of see where they're coming from, right? So here's where they're coming from. There's 2 here, and there's 3 there. There's 5 valence electrons.
So it doesn't matter where you put the dots, right? As long as it's
No, if you kind of make it symmetric, it'll help you later on. But you just better have 5 dots, 5 electrons on there. AS +3. Yeah, good. So for the arsenic +3, you just erase the 4p3. And don't forget to write +3. here's your valence electrons. Two valence electrons. And do the same for silver and silver plus 1. So we're going over here. Oh, don't forget, when you can make D10, you got to do it. So with silver, silver is one of those trick questions. You can make D10 on both silver and silver 1. You can make D10, so make sure you do that. All right? So you don't pull out 2, you just pull out 1. There you go. All right? So make sure you do that. Yeah, I think so.
So that's
This
for
is
this.
quiz 11.
Oh yeah, let's go to the office and fix that.
Will you put that over here so it can be?
Yes, so it has to be, and no commas. So silver. So where did silver go? It's krypton. Right? And then we can make 10. So what did you do? How did you fix this? Annabelle, how did you fix this to make 10? There it is, 5s1, 4d10. That's what you do. Okay, how did you write the Lewis dot symbol for silver? Just put 1 dot. The electron configuration tells you that. There's only 1 valence electron. So just Ag with a plus 1. Oh, sorry, Ag with 1 dot. So the only way to figure this out then Ag plus 1, pretty much just going to remove that 1 dot and the 5s1. So you have krypton, and you could write 4d10. You can write 5s0 if you'd like, but it's not necessary. Ag the plus, right? And then before we go, Melissa's going to tell us which one's larger, nitride or phosphide. She says phosphide. Does everybody agree? The negative 3 part cancels out. She's right. You just compare nitrogen and phosphorus, really. And phosphorus is bigger, according to our trend. He's right. So have a good day.